Let's look at some formulations involving graphs. A graph consists of two sets, a set V of nodes and a set E of edges. Now, given a subset S of the node set V, we would like to define an edge set E of S that consists of all edges E, I, J, such that I, J are an element of S. So if we have here the set of all nodes, so there can be nodes everywhere, and then we have some, this is V, then we have some subset S, then E of S are all the edges of the graph that are connecting nodes inside the subset. And delta of S are all the edges Eij, where one node is inside S and another node is outside of S. So for example, an edge that connects this node inside S with a node outside of S would be a part of delta S. Delta I are all the edges incident to a node. A tree is a connected graph with v-1 edges. If we have a graph with 10 nodes and 9 edges and the graph is connected, it has to be a tree. Let's try to formulate the minimum spanning tree problem using integer programming. Not because it's such a great idea, but because we hope to learn something about integer programming in graphs. As input, we have a graph VE and we have a cost CE for selecting an edge E that is part of the graph. Our goal is to find the minimum cost spanning tree. As variables, we have x subscript e equals 1 if edge E is going to be selected. Now we're using E instead of I as index to index the variables. As constraints, we have a binary constraint that all variables need to be either 0 or 1. How can we guarantee that a subset of the edges constitutes a spanning tree? Well, first we need to make sure that we have exactly n-1 edges that are selected. So we say that the sum over all variables has to be n-1. Again, how many variables do we have? We have as many variables as there are edges in the original graph. Let's quickly look at this visualization. We are given a graph here and we would like to create a minimum spanning tree. The constraint that we just discussed guarantees that there are n-1 active edge variables. So we have 1, 2, 3, 4, 5, 6, 7, 8 nodes in the tree, in the graph. Therefore, we need to select 7 edges. But if we just select 7 edges based on the cost, so that means we select exactly 7 edges, then we could get the solution as shown in the middle here. Here 7 edges are selected, but they do not form a subgraph that is a tree. This node here has no edge connected to it, but this node here has 3 edges connected to it. Also, this node here has 3 edges connected to it. There are some arrows here to indicate some direction, but please ignore the arrows for this visualization. What we want is we would like to guarantee that the selected edges form a tree, so as shown in the example to the right. To ensure that we obtain a valid tree, we would like to create a cut constraint. So for all possible subsets of nodes S, we would like to make sure that there's at least one edge that has one node inside the subset and another node outside the subset. And we only consider subsets that are not the empty set nor the full set of nodes. For example, we can take this subset here of these 3 nodes, and we want to make sure that there is one edge, at least one edge with a node in this subset. So for example, this edge here that goes outside of the subset. You can look at this subset here. Again, we have one edge that connects the outside with the subset. But it's possible that, of course, that there are more edges than one going from the outside to the inside of a subset. So if the subset only consists of this one node here, we have 3 edges in the cut set. So we formulate this by requiring that for all subsets S that are subsets of V, but not the empty set or the full set, that all the edges, so we do a sum over all variables xe for all the edges that are part of the cut set of S, so that are part of delta S. And so the sum of these corresponding edge variables has to be greater or equal to 1. Now, you should complain about this. Like, for all subsets S, I mean, how many are these? These are quite a lot of subsets. For each node in the graph, it can be part of the subset or not. So we will have 2 to the power of V possible subsets, plus minus these special sets here. So these are just too many to enumerate for a large graph. So this is correct, and this will definitely be a problem with this type of formulation for large graphs. Now, the objective function is a sum over all edge variables. We would like to minimize the sum of CE times XE. So each edge has a cost, and then if the edge is selected via the variable XE, then the cost is incurred. We call the linear relaxation of this formulation P-cut. Now there's an alternative formulation that tries to eliminate subtours. So for every subset, again, of all the nodes, we would like to make sure that there is no cycle inside the subset, or no subtour. And we can do this as follows. For all edges that are part of this edge set E of S, so all edges that are fully inside this set S, we would need to make sure that exactly or less than S minus 1 edges are active. For a subset of 4 nodes, only 3 edges can be active, and for a subset of 15 nodes, only 14 edges can be active. That is the maximum number. Now, requiring this for all subsets guarantees that the resulting graph will be a tree. We call this linear relaxation of this formulation P sub. Again, we defined p cut as using this cut constraint, and we defined p sub using the subtour elimination constraint. And p cut and p sub are both linear relaxations. So while at the first glance both of these formulations might seem equally impractical, we would like to note that one solution here is strictly better. That means one formulation here is strictly better. P sub is the convex hull of the set of feasible solutions. And P sub is a strictly better formulation than P cut. Let's look at the Traveling Salesman problem. As input, we are given a graph with nodes V and edges E, and we have a cost C subscript E for selecting an edge E that is an element of the edge set E. The goal is to find a minimum cost tour. As there are multiple versions, we would like to clarify that the idea of a tour is a path through the graph that has the same starting and end point. As variables, we have xe equals 1 if edge E is selected, and we have as many variables as there are edges in the graph. All variables need to be binary. So we have, again, a binary constraint that xe has to be an element of the set 0, 1. So as a reminder that delta I are all the edges connected to node I. So by summing over all the edge variables of edges that are connected to node I, we want to make sure with this sum that there are exactly 2 edges that are selected for each node. So that allows each node to have one outgoing and one incoming edge. Looking at this visualization, again we have the input graph on the left, and now what we have is, with the current constraints, is a formulation that would ensure that each node has 2 connected edges that are active. However, as we see in the middle, this is not enough to guarantee that the selected edges form a tour. There can be many cycles that are selected, but these cycles are not connected. So there's like one subtour, and then there's another subtour here, and a third one here. What we would like to have is, we would like to have a tour that is a single tour that goes through the whole graph. And we can do this similar to what we did for the minimum spanning tree. So this was the minimum spanning tree was quasi a build-up for the Traveling Salesman problem. And again, we will have 2 possible ways to formulate this. One way will be using a cut constraint similar to minimum spanning tree cut constraint, and the other one is a subtour elimination constraint similar to the subtour elimination constraint of the minimum spanning tree formulation. Let's look at the cut constraint first. For all subsets S of V, again excluding these trivial subsets empty set and V, we would like to make sure that the following is true. Looking at all the edges that are part of delta S, again, these are all the edges with one node inside of S and one node outside of S. So these are all the edges that connect the outside to the inside of S. So from all these edges, we want to make sure that two or more of them are selected. So this makes sense because any tour in the graph needs to go at least once into the subset and then leave the subset with a second edge. So there need to be at least two edges. However, it's also possible for a tour to go into the subset, go out again, then come back later, and then go out again. But what we can say is that at least two edges need to connect the subset to the outside. The objective function is that, again, is simply the sum over all selected edges, and we would like to sum up over the cost of all the edges that are selected. Now let's look at the subtour elimination constraint. For all subsets of V that have at least two nodes and at most V minus one nodes, so we exclude the empty set, all sets with one node, and the complete node set V. So for all such subsets, we would like that the following holds. Looking at all the edges within the subset, we would like to make sure that at most S minus one of these edges are selected. Now we can again use the names pcut and psub to assign names to the resulting linear relaxations. Here, however, things are different than for the minimum spanning tree problem. pcut is the same as psub, but neither is the convex hull of the feasible points. Let's look at the city exploration problem. As input, we have a city map given as a graph with nodes V and edges E. We are given a vector C that defines the attractiveness for each edge. So for each edge there's a component in C defining the attractiveness. Then we have a vector T that designates the time it takes to walk along an edge. Then we have a maximum time T that is allowed for a walk. Also, we have a designated start node S and an end node E. The goal is to find a walk through the city from the start node to the end node that explores the most attractive edges but stays under the time limit. So for example, you're a tourist and you would like to go from the train station to the Eiffel Tower, and you have 3 hours until your ticket there is valid, and on the way from the train station to the Eiffel Tower you would like to see as many attractive sights as possible. Let's look at this illustration. We have a graph and two nodes are special nodes, the start node S and the end node E. For each of the edges we have a I was gonna say cost, but that's actually the attractiveness. So this is Ci is something positive now, and a time Ti that it takes to traverse the edge, and then the variable Xi, and looking at the variable below, Xi equals 1 again means that the edge I is selected. But also in this formulation we need variables Vj to denote if a vertex j is selected or not. these auxiliary variables will help us formulate the problem. Again, we have binary constraints that all xi and vj need to be elements of the set 0, 1. Then we have a time constraint that t transpose x is smaller or equal to the maximum time. Now this is just a sum written out in vector notation. Then we have connection constraints, and so for these connection constraints we use this set nj, that is the set of edges incident to the vertex j. That's actually the same as this delta j that we defined before. For some reason this notation is slightly different here. Let's look first at the last equation, since that's the one that's not messed up. For the end node E, we would like to make sure that there's exactly one edge that is connected to it, because the end node has to be reached, and there shouldn't be an edge leaving the end node. Similarly, for the starting node, we would like to make sure that there's exactly one edge connected to it. So this needs to be moved under here. And then for all the other nodes, we would like to model that there are either 0 or 2 edges connected to them. That is why we have these auxiliary variables vj that tell us if a node is selected or not. So if a node is not selected, then vj equals 0, and the sum of edges connected to the node has to be 0. If the node is selected, then the sum of edges connected to the node has to be 2 vj. That means exactly 2. The objective function is that we would like to maximize C transpose X. Similar to the examples that we discussed before, minimum spanning tree and traveling salesman, this formulation can create cycles. They're again the same type of solutions that can be used. Similar to before, we could use some constraints that forbid cycles. But alternatively, one can use a method that lazily adds constraints. So one could just solve this problem, then check for cycles, and then lazily add constraints that explicitly forbid all the variables to be selected simultaneously that form a cycle. The same solution also applies to other graph problems, where the idea is that one doesn't specify all the required constraints, then solves, observes if an invalid solution was proposed, and then add constraints to explicitly forbid the invalid solution. Next, my colleague Jihan will talk about some more advanced